Welcome to the 20th video of Quantum Mechanics Done Right, the shortest path from novice to researcher. In this video, we're going to be talking about time evolution, and you can't do time evolution without the work of this gentleman, Hale Trotter, who is the person who first figured out how the Trotter product formula works. Chapter 14, Time Evolution. In quantum mechanics, time evolution is really still an active field of research. Not so much for single particle problems, but for many body physics, there's lots of intriguing and interesting things in time evolution that we don't really understand well, and we don't even have good methods to numerically solve these problems, which is why it remains an active area of research. The way that we start time evolution in our work is with the Trotter product formula, which then leads us to what's called the time-ordered product. When you write it in the Trotter product formula form, it's completely obvious why it is a time-ordered product. With the way that most textbooks derive it, it's really hard to understand why it's called a time-ordered product, and then you really don't understand exactly what the object is that you're working with. We then apply this approach to solving the problem of magnetic resonance. This problem can be exactly solved, and the way that it's solved with the Trotter product formula I think is particularly cool. It's a lot easier than going to the rotating frame, which is the standard way that it's done with differential equations. It actually just naturally comes out that you work and get the result in the rotating frame just by working with the Trotter product formula and our identities, particularly the Hadamard lemma and the BCH formula. So it's very cool the way that this works out, and I think you'll enjoy seeing how it is done. And then when you get the final formulas, because we know exponential disentangling, we can actually evaluate them for arbitrary spin, and I haven't seen any textbook that actually does that. Next, we look at the harmonic oscillator. Our focus here is primarily on coherent states and squeeze states, and they have very simple time evolution, so it's easy to work them out, essentially, again, using our operator identities like Hadamard lemma. We then look at the free expansion of a Gaussian, which is actually can be thought of as the expansion of a very particular squeeze state. Then we get into some formal development, looking at the interaction representation. That leads us into solving the Landau-Zener problem. While there is an analytic solution to this problem, it's very complicated, and instead we talk about how you would solve it numerically by looking at the time evolution of individual steps, but it turns out that's not enough to get it right. You have to actually put in some asymptotic behavior that comes from time-dependent perturbation theory, which we get by looking at the interaction representation. So it's a nice application of the interaction representation to be able to get results that work properly. Next, we look at the driven harmonic oscillator. This is a fantastic problem. I really like this problem. It is a highly non-trivial time evolution, but you can solve it exactly. There are two different ways we can do it, one which is based on the BCH formula, and one which is based on applying our operator identities. That second method, using the operator identities, I've not seen anywhere else. The method of using the BCH formula is very similar to the way that Merzbacher solves this problem in his textbook. And then we end the chapter with a section on the Ising model and the stroboscopic XY model. This shows how you can simulate an Ising model in a particular regime of parameters, and then if you measure the properties of the model at very specific times, it will look like the XY model. And it's really intriguing the way you get this mapping between the two, and this is an idea that was used in ion traps to try to simulate the XY model. All right, let's go browse through the chapter. Our quote for this chapter is from Samuel Jackson, an actor. "Everybody has to learn that the world works in very specific ways, and you're not in charge of it." I just love that quote. It's really important, not just for quantum mechanics, it's important for life. All right, as I said, we start with the evolution operator for the time-dependent Hamiltonian. The way in which this works is we need to preserve probability. That tells us that the time evolution operator must be unitary. There's another property called the semi-group rule, which says that if I time evolve from T1 to T2, that's the same as evolving from T1 to T3 and then from T3 to T2. And that requires the time evolution operators satisfy a certain functional relationship. It turns out the simplest way to get that to work is by an exponential whose argument is proportional to time. Then, because we want the time evolution to be governed by the Hamiltonian, that tells us what the operator has to be. And then finally, there's an overall sign that needs to be picked, and that's picked by convention. And then we just have discovered what the time evolution operator is. Then if we have something that's a time-dependent Hamiltonian, we just approximate it by a time-independent Hamiltonian for a small time step delta t, and then we just build up our time evolution operator by taking the results for each of those different delta t's and multiplying them together. And that's what's called a time-ordered product. And here's Hale Trotter. He's the person who first worked out the important identities that we're using that are involved in the Trotter product formula. Time evolution of Hamiltonians that are constant in time is relatively simple. There are some subtleties to it, but it really is not a very complicated thing. It's when you get into the time-dependent Hamiltonians and you're trying to look at their time dependence that things become quite a bit more complicated. So now we get into magnetic resonance, and magnetic resonance is the domain of this person, Isidore Rabi. He's the person who essentially took the ideas of the Stern-Gerlach experiment, moved them into experiments on atomic beams, and really, I would say in many respects, his work started the second quantum revolution in the sense that he was able to really control quantum states by doing things like playing with magnetic fields or electric fields or different kinds of pulses. And the way in which he worked all of these ideas out is really spectacular work. And it took place primarily in the 1940s and even 1930s. So he really was ahead of his time in the things that he did with quantum mechanics. The work that he did could comfortably sit in what we currently call the second quantum revolution. We use a lot of the ideas that he developed in the second quantum revolution. So what's neat about this is by using our operator identities, we can get an exact formula for the time evolution that's relatively simple, and we can just evaluate it. This is showing you what that formula is. And it's kind of cool the way all of the elements, all of our operator identities, and all of the ways that we do things all come together in a beautiful way to make everything work very easily here. There's another interesting problem in time evolution that involves something called the geometric phase or the Berry phase. And magnetic resonance is a great problem to look at the Berry phase. So we talk about the Berry phase toward the end of this section as well. There's a lot of cool stuff associated with the Berry phase. There's some problems that we have on it. If you've ever wanted to know what the Berry phase is, well, we really cover it here and you get a good idea of what a Berry phase is. Then we move on to just a short discussion of how what we just did for solving the magnetic resonance problem relates to nuclear magnetic resonance and magnetic resonance imaging. This is a relatively short chapter. There's not a lot in it. Short section, I mean. There's not a lot in it. Then we go into how we do the Trotter formula for the time-dependent Hamiltonians. And here's where we get into lots of complications. Things are a lot more difficult to work out. We have to bring in the BCH formula. And formulas get a little messy here. So you just got to stick with it to be able to go through and work through it. We talk about things like circuit compression in quantum computing, which is an interesting idea that is related to using our exponential disentangling identities, but it's even more powerful than just the disentangling identities that we use. And there's a number of other ideas that are quite interesting that we bring up in this chapter, particularly in the problems. That was an image of a coherent state. I'm going to actually come back to this. I'd like to talk about this a little bit. I love this image in 14.5. This shows us wave-particle duality. The solid figure is telling you what the probability distribution is. The area of each slice is the probability density. The wave, because it's a complex wave, is that windy line that goes around. You can think of the fact that that's like got a bulge there, that the thing looks like a particle, but it actually has this wave completely intertwined in its definition. And you can't separate the wave properties from the particle properties. They're totally intertwined into one another and inseparable. And it's a beautiful way of visualizing wave-particle duality. Okay, the time evolution of coherent states and of squeeze states turns out to be a relatively simple thing to do. And it really just uses the Hadamard lemma to work out the results. We have some nice images here that illustrate things. And we talk about something called a Schrodinger cat state, which has this really beautiful interference pattern that you can get. And it's just kind of cool how you can take something that had this wave-particle duality, but in general looked like a particle, but by carefully preparing the right state, you can make it have interference effects that show us the wave properties in a way that are very easy to see. The only challenge here is, of course, you have to do an amplification of the signal so that you can take what's happening on the quantum mechanical scale into what's happening on a macroscopic scale so that you can actually detect it and measure it. And this has actually been done in ion traps. So this stuff is not, stuff of fiction that is just a thought experiment. They're real experiments that have imaged these so-called Schrodinger cat states. We then go on to the free expansion of a Gaussian wave packet. This is a problem you'll see worked on in pretty much every textbook. The way that they do it is really calculus heavy and very messy. The way we do it is, of course, operator heavy. Yeah, maybe it's a little bit messy, but I think it's not as bad as it is in the calculus-based way of doing things. We kind of have a real clear pattern and way that you can do the problem to make it work. There are these beautiful recent experiments that have come out of Cindy Riegel's group that have imaged the wave functions of the harmonic oscillator, the ground state, first and second excited state. And we talk about how those experiments work and how those images were made. I find this kind of stuff with a harmonic oscillator and free expansion, really cool stuff. We then look at how you can factorize the evolution operator. That's essentially what the interaction representation is. This factorization is actually a very simple thing to do. Sometimes textbooks make a big deal about the interaction representation. It's really a pretty simple concept. Once you have the interaction representation, you can then do an expansion of one of your factors in a power series, and that's what perturbation theory is. So we look at that expansion as well, because we'll be using that in the next chapter when we talk about the Landau-Zener problem. So here it is, Landau-Zener problem. Landau-Zener problem was worked out actually by these four people in the same year. I think it was 1933. So you have Landau on the left, you have Zener next to him, then you have Stuckelberg, and then you have Majorana. Stuckelberg is an interesting guy. Apparently he solved QED like 5 years before Schwinger and Feynman and Tominaga, but he never really fully published his works, and so he kind of gets lost in the history. Majorana is a very interesting person. You might have heard of Majorana particles or Majorana fermions. They're something that people are desperately looking for to try to do topological quantum computing. Majorana has an interesting history. He just disappeared, I think in the mid-1930s. He got on a ship and then no one saw him again afterwards. All four of these people wrote a paper on the exact same problem in the exact same year and had different ways of approaching it. Zener's approach was the most exact. He really solved the problem exactly all the way through. Landau's paper was one that was very physical and had nice arguments motivating why the behavior was the way that it was. The Stuckelberg and Majorana papers are also quite interesting in the way in which they work through the materials. So there's lots of interesting stuff here on this Landau-Zener problem. It's a problem where you essentially are switching from one state to another state, and how fast you do the switching determines how complete you actually get the system to switch. And from numerics, it actually turns out to be a very difficult problem to solve accurately. But if you put in the right perturbation theory to describe what happens at long times, you can get incredibly accurate results. And so this chapter talks about these issues. We had written a paper about this about 2 years ago that talked about these details. Now we get to the driven harmonic oscillator. I absolutely love this problem. It is one that really brings in a lot of our operator ideas and allows us to solve it. There are two ways to solve the problem. One that's very BCH heavy, and this approach has been done in Merzbacher's book. It's really doing by hand what's called a Magnus expansion. Magnus expansion is a nice expansion to know about. There also is another way of doing it that's very operator heavy, that doesn't require any of this Magnus expansion, and it's pretty cool to see how that works. We take you through the details of that in one of the problems. Then we get to a problem that is in almost every quantum textbook, the photoproduction of hydrogen. This is looking at the transitions between excited states and the ground state, or different excited states, and how you work out the details of how that comes about. By the time you finish the calculations, you actually are calculating the lifetimes of the states. And so lifetimes are related to the line width. So this is a way that we actually determine the shape of the spectra by doing a quantum mechanical calculation. This is showing you an image of what a line width looks like of a spectral line. And it's a really important series of calculations that anyone who's gone through a quantum mechanics class should be comfortable doing these kinds of calculations. And then our final section looks at how you can simulate an XY model in an ion trap by simulating an Ising model, but looking at the problem at specific moments in time. This uses something called a rotating wave approximation, which is a very important approximation. We've already discussed the rotating wave approximation a few times in the book, but here we discuss it again, and it's a really important concept. What it essentially says is when you have something that is oscillating really fast, typically you never get anywhere due to those fast oscillations. So you can sort of average over those fast oscillations and look at the slower dynamics of the system. It's related in many respects to the quantum Zeno effect as well, but it's a very common approximation in atomic physics. It's used all the time. And so we go through how that rotating wave approximation works and how that allows you to do this mapping between the Ising model and the XY model. The mapping is not perfect. There are some issues with it, and we discuss a lot of those details and subtleties and nuances in this work. We get some beautiful pictures about how those different approximations work for the Ising model and for the XY model. And that takes us to the end of the chapter. Hey guys, let's do quantum right.